Hi, in this video we're going to look at the integral test for series. So our goal here is to show how we can determine the convergence or divergence of our infinite series n equals 1 to infinity, technically n equals anything to infinity, and how that relates to its improper integral. So the rule here is that if we have a series Fn, we'll say n equals 1 to infinity, but it could actually be any number that we start with. This converges if the integral from 1 to infinity of f of x dx converges. And the same thing for diverges. So it converges if the integral converges, and it diverges if this integral diverges. Okay, and this is pretty much it. So let's go ahead and look at a couple of examples. So let's start with our favorite divergent series, n equals 1 to infinity of 1 over n. So let's look at how this actually diverges using the integral test. So what we're going to do is we're going to translate this to the integral of a continuous function. So we're going to be looking at the integral from 1 to infinity of 1 over x dx. And we know that this diverges. So if we want to look at this real quickly, this is the limit as b goes to infinity of the integral from 1 to b of 1 over x dx, which is the limit as b goes to infinity of 1 over, or not 1 over, the natural log of the absolute value of b minus the natural log of the absolute value of 1. And this is the natural log of infinity. So as we get bigger and bigger, our natural log just keeps growing. And so this is infinity. And we just have to check to make sure that the natural log of 1 isn't negative infinity. Otherwise, we'll have to use some L'Hopital's rule or something like that. But the natural log of 1 is just 0. So it's infinity minus 0, or just infinity. So we know that the integral diverges. So since the integral diverges, we can say that the sum diverges. Okay. So now let's see why. So let's look at this visually. And if we take a part of the graph, thank you Desmos for the graph, this guy over here is our 1 over x. So this is our continuous function. And then these boxes here are our 1 over n. So the shaded boxes are 1 over n. And we can see that 1 over 1 is 1. 1 over 2 is 1/2, 1/3, 1/4, 1/5, and so on. But the important thing to note here is that the area under the curves of this step function are actually bigger than the curve. So each of these has base 1 and height 1 over n, so its value is 1 over n. And adding up 1 over n, so if we look at the sum of 1 over n, so the sum of 1 over n from 1 to infinity is actually bigger than the integral from 1 to infinity of 1 over x. And since this diverges, so this goes to infinity, that tells us that the sum of 1 over n from 1 to infinity must also go to infinity. Now let's look at one that we know converges. So let's take a look at the sum of 1 over n squared as n goes from 1 to infinity. Okay, so if we were to draw this, let's go ahead and try to do a hastily drawn graph here. 1, 2, 3, 4, and this, I guess, will be like 1, 2, 3. So 1 over 1 squared is going to be 1, so that's going to correspond to this rectangle. And then 1 over 2 squared is going to be 1/4, so maybe like here, and then 1/9. So it's going to be even smaller. So this is our 1 over n squared. And then let's just go ahead and get some blue. And let's just sketch 1 over x squared real quick. So it should look something like that. Okay. And doing this, we see that this is about 1 over x squared. So if we look at the sum of 1 over n squared from, say, n equals 1 to k, that's actually going to be less than the integral from 1 to k of 1 over x squared dx. And then when we pass to the limit, so now we'll take the limit as k goes to infinity, we'll see that the sum as n equals 1 to infinity of 1 over n squared is actually less than the integral from 1 to infinity of 1 over x squared dx. Okay. And remember that the integral of 1 over x squared is actually 1, right? Because 1 over x squared integrates to negative 1 over x from 1 to infinity. So it's going to be negative 1 over b, the limit as b goes to infinity, minus negative 1 over 1. And so this goes to 0, and this guy is actually just equal to 1. Okay? So that tells us that this guy converges. So the sum from 1 to infinity of 1 over n squared converges. And we don't know what it converges to here, and improving it actually is quite a bit of work, but it converges to pi squared over 6, I believe. And this is an important thing to note here, because this is different than 1, right? So even though the sum converges, it does not converge to the integral. And that's an important thing to know, that the indefinite integral tells us if it converges or diverges. It doesn't tell us what it converges or diverges to. So 2, maybe it's pi squared over 6. It's been a while. All right. So that's pretty much all that we have for this. So let's just do one more example, and let's determine if, so we want to know, is the sum from 2 to infinity of 1 over n log of n convergent or divergent? So we're just going to ask if it's convergent. Okay, and we're just going to use the integral comparison test, because this actually turns into a pretty nice integral, right? So we integrate from 2 to infinity, so we have to match our lower bound with our lower bound, of 1 over x log of x dx. And when we do that, we can make a u substitution. So u can be equal to the log of x, and du is going to be equal to, what's that, 1 over x dx. So the log of x transforms this bottom guy into the log of 2. And then the top part, the log of infinity, is still infinity. And then we have 1 over u du. And so this guy is actually going to turn into the natural log of the absolute value of u from the log of 2 to infinity. And now we're concerned about convergence and divergence. So we don't actually care what number it converges to if it converges. So we're going to be looking at the log of b, and we'll take over here the limit as b approaches infinity minus the natural log of the natural log of 2. Well, natural log of 2 is a number, and it is non-zero, and it's non-negative. So this guy is actually just a number. So what we really need to know is, does this converge or diverge? And we already saw that it diverges. So this is going to be infinity minus a number, which actually just turns into infinity. So we can say that this diverges. And when we say it diverges, we can say it diverges by the integral test. All right, we can do one more example. So let's look at the sum from 0 to infinity of ne to the negative n squared. Okay, so as always with all these integral comparisons or integral tests, we're just going to look at the integral from 0 to infinity of x e to the negative x squared. And when we do this, we let u be equal to negative x squared. Du is going to be negative 2x dx. So we're just going to have to throw in a negative 2 here, and we're going to divide it by negative 1/2 on the outside. And what we end up getting, negative 0 squared is going to keep this a 0. And then negative infinity, as we approach infinity squared, is actually going to be negative infinity. So we have negative 1/2, the integral from 0 to negative infinity of e to the u. Right, so e to the u du. And we can actually just switch the bounds and change the sign of our integral. Right, so we can change this to 1/2 the integral from negative infinity to 0 of e to the u du. And now we just evaluate this integral. So 1/2 e to the u from negative infinity to 0, which is going to be 1/2 e to the 0 minus the limit as, let's say, a goes to negative infinity of e to the a. And by doing this, we see that we have 1/2 times e to the 0 is 1/2, that's just a number, minus e to the negative infinity goes to 0, so that's 0. So this converges, so our integral converges, which tells us that our sum converges. So we can say that the sum converges by the integral by the integral test, right? By the integral test. All right. As always, thank you for watching. If you have any questions, comments, or concerns, leave them in the comments below. That's all I got for you guys today. Next time we'll talk more about sequences and series.